Welcome to the presentation of ICAICT 2020, Second International Conference on Advanced Information and Communication Technology, United International University. Firstly, I would like to thank ICAICT 2020 for organizing this conference virtually because of current pandemic situation. Special thanks to the conference chair and congratulations to all the authors. The title of our paper is LULC Classification by Semantic Segmentation of Satellite Images using Fast-FCN. Here is a list of the authors who worked in this project. Let's look at the content overview, that is how I will be covering the presentation. We will first talk a little about our objective, then we will state the general outcome of our work with some visual results. Then we will explain the methodology along with our contribution. Afterwards, we will see a comparison of our work result with a readily available software and another segmentation method. Then we will see what are some limitations of this network. Finally, we will show some possibilities for future work. Objectives. Our main objective was to propose an automated LULC classification method that might outperform some conventional techniques. Another objective was to show a comparison of evaluation metrics with a readily available software eCognition and another segmentation technique named FCN 8. There are other segmentation methods working on Gaofen Image Dataset, but we only showed two for simplicity. Outcome. The first image is original resolution of RGB satellite image. This is the test result and this is the ground truth. Ground truth is the image of what the annotation is supposed to be, and test result is the predicted annotation by the network. Even if we look closely, we can't really differentiate between the test result and ground truths, as the evaluation metrics are almost more than 95%, which again shows the credibility of this procedure. There are actually 5 classes here: forest colored as cyan, farmland colored in green, water colored in blue, BuiltUp colored in red, Meadow colored in yellow, and unrecognized class colored in black. Where we weren't sure about the class was marked as unrecognized. Here is another example of our test result. In both cases, this is visually almost impossible to test the difference. Let's look at the methodology of our work. I'll try to be as precise as I can so I don't take any extra time. Firstly, we start with 150 high-resolution RGB satellite images. They were split into two groups, 120 for training and 30 for testing. In the training, 120 images were fed into the grid block. Both the annotation, ground truth, and the images were fed into the grid block. In grid block, each image was grid into 182 sub-images, keeping the record of the position. The reason for introducing this block is to preserve the pixel information. Originally, when the images are fed into the network, it downsamples the images, which results in loss of pixel information. This block might reduce it by a great factor. Then the images are prepared and pre-processed before the augmentation process. Here mainly the RGB values are normalized to 1. In data augmentation process, each image was rotated 180 degree, 90 degree and 270 degrees. Then the training was started. It took 39 hours on a Tesla K80 48GB graphics card and 120GB RAM to finish in 50 epochs. The trained work was saved on local drive. Then for testing part, the 30 high-resolution images were pre-processed and then fed into the Fast-FCN trained model. This model gave the corresponding prediction. After receiving the predicted annotations, they were stitched back together in the original place to recreate the high-resolution satellite images. Now these predicted annotations and ground truths are used to pixelized calculate the values of evaluation metrics, that is, accuracy, IOU, precision, and recall. Now let's see some comparison. This table represents the comparison of evaluation metrics between ungraded FastFCN and eCognition software. Here it's easily visible that even without the grid block, it outperforms eCognition by vast margin. This table shows comparison between FastFCN and one of its competitor FCN8. Both procedures contain grid block in them. Values of evaluation metric shows that FastFCN also outperforms FCN8 by all the classes. Now let's check out some limitations of our work. Here we separated the corrected part from the error by red marks. The white part are the parts where the network predicted the class correctly, and the red marks are the part where the network failed to predict the correct class. If we look closely, we can see the sharp edges are the part having most error. Secondly, because of unbalanced class chaining, some classes were more error prone than others. The texture and color variation of meadow and forest were similar, and in some cases where the prediction came out all wrong, the neural network confused between these two. Here's the original image, and here is the ground truth, saying all these parts are of meadow. The test result came and they predicted all these parts as forests. That is why this red mark shows all these places were wrongly classified. Future possibilities. Let's look at some future possibilities and scope for future works. Firstly, we can work with bigger dataset that might give us more insight into the errors. Then we can incorporate different type of augmentation methods. We only used rotation here. We can use saturation, hue, lighting change along with upscaling and downscaling. We can introduce more LULC classes along with the 6 we already introduced. We can compare with other existing segmentation process. We have only compared with FCN8 and eCognition, but there are also many segmentation process already available and still developing. We can use these results to compare with them too. And by this, I'd conclude my presentation. I once again thank you all for staying with me.